Okay, so for this one, we are asked to find y and x. The one thing I didn't put up here, this comes right out of your packet, by the way, is that slope factor is 1, 1. This is number 43 out of your packet. What that 1-to-1 slope tells us, if I'm looking at this piece here, to make those slope factors work, we have to find right triangles. We have to find triangles that have sides that are one side vertical and one side horizontal. And as we're doing trig this semester, that's one of the things that we have to do a lot, is to find right triangles. And even though we're not to the trig yet, two of our biggest tricks for finding right triangles occur in this problem. One of them is the intersection of vertical and horizontal dimensions. And that's what we have here. We have a vertical dimension and a horizontal dimension. Where their intersection is, there's going to be a right angle there. The second thing we look for is the radius of a circle. To a tangent. We'll get to that second example here in a little bit, but let's use this first one right now to find the missing dimension. We know that this dimension here is 0.200. That's from right there. What's this dimension here have to be? Well, 0.250 minus y, or from the triangle, we know it has to be 0.200. Why? Yeah, it's 1-to-1. So vertical and horizontal have to be equal. Now that we know that that's 0.20, y has to be 0.05. Just the 250 minus the 200. Now that we have that dimension there is 0.05, we can look inside our circle here. There's the center of our circle. We've got a radius there, which is, of course, half that diameter. That's 0.075. I'm going to leave the inches off for now just because it's going to clutter it too much if I put an inch symbol on every dimension. That's a right angle there because that side's tangent. This is a right angle here because that side's tangent. That's also 0.075. Well, what is the slope factor on that? Well, we talked about this briefly last semester. Parallel lines have the same slope. Perpendicular lines have opposite reciprocal slope. What's that mean? Well, that means if there's my graph, if I have a line that goes like this, let's say it's at a 2/3 slope, the line parallel to that, not parallel, perpendicular, going at a right angle. First of all, the brown line has a positive slope. The green line has to have a negative slope. That's the opposite part. Reciprocal means you exchange numerator and denominator. So this is a -3/2 slope. Well, over here, this slope is a positive 1/1. This slope here, being perpendicular, has to be a -1/1. In other words, the aspect ratio on that line is also 1-to-1. Make sense? Now, because of that, we can draw in this triangle. I'm going to call this dimension A, this dimension B. finding dimensions A and B are going to be key in solving this problem. How do I find dimensions A and B? Well, I know that this is a 1-to-1 ratio. So that A and B are the same thing. So I'm just going to call them both A and A. Yes, and I know that this is 0.075. So I know that A squared plus A squared equals 0.075 squared. He lives. Feeling better? Good. So now A squared plus A squared is 2A squared. 0.075 squared is 0.005625. So to solve this, what do we have to do? Divide by 2. So I divide by 2. And then, so we've got A squared equals 0.0028125. Square root it. So A equals, what's the square root of that? 0.053, we're going to round it to. So we'll round to 0.053. So that means this is 0.053 inches in both directions. So let's take a look and see how this works. So 0.053. Okay, well, this is still a 1-to-1 slope. If I know the distance from here to there, I can find that rise, can't I? How do I find that distance? Well, I have this distance plus that distance will be that total distance from here to there. And I can subtract off 0.05. So I have here, oops, wrong tool. There we go. So I have the 0.075 and the 0.053. So that's 0.128 inches from here all the way to there. I only want from here to there. So I'm going to subtract off the 0.05. Gives me 0.078 inches. So from here to here is 0.078 inches. That makes this height 0.78 inches. So from here to here, 0.078. From here to here, 0.053. And from here to the very top, 0.075. So what we have there is 2.06, I believe that all adds up right, total. Or 0.206. Does that end up right? So that being 0.206, up here is 0.200, so the difference is 6,000 of an inch that sticks up. Well, that's nothing. That's nothing yet. Any questions? The key is this aspect ratio. And knowing that since this is perpendicular, we have that opposite reciprocal. That the slope is just, you switch the vertical and horizontal dimensions. Let's flip backwards in our packet a little bit and talk about problem number 36. Does anybody have an answer to problem number 36 yet? 4 point, what is it? Something's a little off there. Yep. Let's take a look. So this is a standard Morse taper. We've got this ball with a 1.2 inch diameter. We have the mouth of the hole here is 1.231 inches across. We want to know, well, what we're going to find basically is how far the ball sticks out. What we really want to know is how far it is from the top of the ball all the way to the bottom of the block, but that'll be easy to find if we just know this dimension. So I'm going to call this dimension here y. This is the x that we're trying to find. It doesn't look like there's much information here, but there really is. This is a number 4 Morse taper. A number 4 Morse taper is 0.62326 inches per foot. Change in diameter. Now I can change that into an aspect ratio if I wanted to. I could divide this by 2 to get a 0.31163 inches in 12 inches. Aspect ratio like that. I changed the foot to 12 inches. I divided this by 2 so it's a radius instead of a diameter. And technically I got that backwards. This should have actually been down here because it's this aspect ratio right there. Make sense? So now, we've got this ball here. Has a radius, 0.6 inches. Gotta find those dimensions right there. It also will have an aspect ratio of that. It's just going to be inverted, right? If I call this A and B, the ratio of A to B is just going to be this ratio. Of course, this is going to be the vertical. It'll be 0.31163, 12, like that. So here's what I'm going to do. We remember this aspect ratio looks like a right triangle. I'm actually going to treat it like a right triangle and complete it. I'm going to find the length of that hypotenuse. The length of the hypotenuse would be the square root of 0.31163 squared plus 12 squared. That's just a squared plus b squared equals c squared. I just rearranged it a little bit. So the square root of 0.31163 squared plus 12 squared. 12.004 is what that comes out to be. So now what that's telling me is up here, I can find A and B. I have the 0.6 relating to the 12.004. 0.6 to 12.004 is the same as A to 12, because A is horizontal, 12 is horizontal. So 12.004, oops, clear that out. How about 12 times 0.6 divided by 12.004? So I said 0.5998. So this here 0.5998 inches. B can be found in the same way. 0.6 is to 12 as B is to 0.31163. 31163 times 0.6 divided by 12, 0.04. Could put the 0.004 on there. I get 0.0. Holy crap. 0.0156, something around that too. That's that dimension. Make it a little clearer so my one don't get lost there. So what's that telling me? Well, across here, from here all the way to here, which is the point of tangency, that's where it touches this slope here, right? That whole thing is going to be double that. 0.5998 times 2 is 1.1996. So now I can use that along with my Morse taper, find the distance from here to here. How so? Well, the original diameter of the hole is 1.231 minus that point of tangency, 1.1996. So I put in the 0 there, and we subtract. So we get 0.0314 is my difference in diameter. So then my Morse taper, 0.62362, 62326, sorry, over 12, that's going to be 0.0314 over whatever that depth is. So we'll cross multiply and divide. 12 times 0.0314 divided by 0.62326. I get 0.6046. So that is the distance from here to that point of tangency. So why is that important? Well, because what I'm going to do is I'm going to find the distance from here up to here and then subtract that distance. It'll tell me how far I'm sticking out of there. It's going to give me y. This is 0.6 plus the 0.0156 makes that total 0.6156. We'll subtract from that 6046, which gives us 0.011. Now that's why. To find x, which is that total height, we were given that this was 4 1/8 inch here, which is 4.125, plus the 0.011 is 4.136 inches. That's the total height. Not so bad? Little off? What's an inch or two among friends, right? What are you guys thinking? Fun stuff? Yeah, come May. Let's look at number 40, actually. How many of you got number 40 done? What'd you get for size on D? On D. Pulley D. Let's take a look and see how we did. I'm going to draw it just a little bit simpler for myself to make it easier on me. Basically the same pulley system. I'm just looking at it from the very side instead of straight on. We start off, this is a 4-inch pulley. The big one here is a 6-inch, small one's a 3-inch. Going to, we don't know this size. We're asked to find the size of the pulley, whether diameter or radius, whatever. Usually we'd find a diameter because the rest of them look like they're diameters. It does say that this is 1300 RPM here. And this first one is starting at 1800 RPM. Well, if that's 1800 RPM, how do I find the RPM on the 6-inch gear? Remember, it's size times speed. 4 inches is turning 1800 RPM. So that's going to equal 6 inches times whatever that RPM is. So 4 times 1800 is 7200 equals 6x. We divide by 6. You get 1200 equals x. So that means this is moving at 1200 RPM. Makes sense. Bigger pulley can turn slower. How do we find the speed of the 3-inch pulley? Very good. They are on the same shaft, which means they must have the same RPM. The change in RPM only works if they're connected with a belt. They're on the same shaft. Those both are 1200 RPM. So that means that starts out as 3 inches times 1200 RPM equals 1300 RPM times D, or D times 1300 RPM. However you want to look at it. 3600 equals 1300 D, and we divide by 1300. Gives 2.769 inches. Sounds like you had it right up to the end. Something went wrong the last time. Sounds like you went the wrong direction with this. You might have switched the 13 and the 12 or something there. If we look at like number 56. We have pulleys A and B. And it says pulley B turns 7 times for every turn of pulley A. Now that's not RPM, is it? But we're going to use it as that. 1 to 7, 1 RPM to 7 RPMs. Because it's not the actual amount of RPMs that really matters, it's the ratio of RPMs. This could be 100 RPM to 700 RPM, doesn't matter. Now obviously my drawing is off here because the smaller one would be turning faster. But anyway, let's take a look at the sizes here. Pulley A has a 4-inch radius. Find the radius of pulley B. That is radius, should be labeled so we don't think that is a diameter. So anyway, that's going to be 4 times 1 equals the size of B times 7. 4 times 7 is 4 equals 7B. And we divide by 7, which is going to give us 0.571428571 approximately inches radius. Approximately. Any questions? So some things we haven't talked about yet. Mechanical advantage. One of the biggest things in mechanical physics is mechanical advantage. Most of the tools we use are designed for some sort of mechanical advantage. A hammer. The whole purpose of a hammer is mechanical advantage. Now, a hammer actually has an inverse mechanical advantage because the force that you apply to the hammer is less than the force that the hammer applies. Now, that sounds weird because you think of using a hammer to hit things hard. But in a hammer, you're not gaining force. What are we gaining in a hammer? Speed. You move your hand at a slower speed with a greater force. The head has less force, greater speed. So mechanical advantage is output force to input force. Most of the time, that mechanical advantage has to be larger than one. You're getting out more force than you're putting in. The loss is speed or distance. For example, a lever or a lever, depending on who you're talking to. But if I want to lift something, let's say I have a heavy object here that I want to move. I can set up a fulcrum, a pivot point for my lever, and a lever now if I push over here, if I push down on this, this is going to push up with way more force than what I put down on it. What's the trade-off? Yeah, if I push from here all the way to there, this is only going to move like that far. I have to move a lot further, but I have to apply less force. So let's say the force I apply here is 100 pounds of force, and the force that this lifts with is 400 pounds. My mechanical advantage, the abbreviation for output force is F out, and input force is FN, is 400 pounds to 100 pounds, or a 4-to-1 mechanical advantage. We usually just say that because mechanical advantage is always written as a unit ratio. We usually just say that that's a 4, mechanical advantage of 4. Another type of lever is a wheelbarrow. You ever notice that if you load the wheelbarrow up all the way up here, it's really hard to lift? So what do you do to get around it? You load it heavily up front. The reason for that, now the load, the center of that load is closer to the pivot point. So when you lift here, this is moving up less distance. The further that load is up here, the further that load has been lifted up when you lift it. When it's above the wheel, it barely moves up. It takes very little force. In fact, if your load was perfectly centered above the wheel, you could lift it. All you'd be lifting would be the weight of the handles. You wouldn't be lifting any of the weight of the load. The wheel would be fully supporting it. Makes it really tough to balance, so if you do that. So let's say this here is 1 foot from the wheel, and where we're lifting is 5 feet from the wheel. If we load 200 pounds in there, how much force do we have to lift with? Well, our input force is 5 feet away from our output force of 1 foot away. We're going to lift 200 pounds. 1 times 200 divided by 5 is 40 pounds. So it only takes 40 pounds to lift 200 pounds with that ratio of length. Yeah, that's what skid steers are for. Or pump trucks. If I had to move more than about 50 yards with concrete, well, not even, more than about 20 yards with concrete, is always pay the money for a pump truck. So anyway, that's how those work. The next thing is circuits. This would be like problem 75, 76 in your packet. So let's say you have a 24-volt circuit, and you have resistors here. 4 ohms and 2 ohms. In a series circuit, how do I know it's a series circuit? Because when you start, what's that? Yeah. If you start at the voltage source and you go around the circuit, there's only one possible path, and that path takes you through both resistors. So it's a series. A parallel circuit would look like this. So if you leave the voltage source and go around, there's 2 different paths you could go. And each path only takes you through one of the resistors. That's parallel. We'll talk about that in a minute. Okay. And it's only took me by surprise. In a series circuit, the current has to flow, the same current has to flow through both resistors. There's only one path. So the current is constant. What is divided is the voltage. So the voltage is split. There's 24 volts produced. There has to be 24 volts dissipated. The ratio of voltage dissipated is the ratio of the resistors to total resistance. So 4 plus 2 equals 6 total ohms resistance. So the voltage across this one is 4 out of 6 equals how much out of 24? Cross multiply and divide, that's going to be 16 volts. So there's 16 volts dissipated in that resistor. This one down here is 2 ohms out of the 6 ohms total. Out of 24, if we cross multiply and divide, 2 times 24 divided by 6, that's 8 volts. Down here, the current is divided. The voltage is constant. So what that means, let's say this is a 24 volt circuit. And let's say we have R1 here is 4 ohms again, and R2 is 2 ohms. Now the voltage across each of those is going to be 24 ohms. Stays the same. To get the current in one, the current is voltage divided by resistance. So this one's going to be 24 divided by 4. That's 6 amps. This one here is 24 divided by 2. That's 12 amps. Now you'll notice up here, the ratio of voltage was a direct ratio. The bigger resistor dissipated more voltage. Smaller resistor dissipated smaller voltage. Down here, it's an inverse relationship. Bigger resistor had less current. Smaller resistor had more current. Make sense? Okay. No? It's that inverse relationship. So up here, bigger resistor, more voltage. That's why we're able to use this proportion. Resistance over total resistance equals voltage drop over total voltage. Down here, if I wanted to use the resistors, I would have to do 4 ohms times whatever that current is there equals, and I'd have to have a fraction now of the total voltage drop. But it's going to equal this one, 2 ohms times whatever that current is there. So I need to know one of the currents first. If I know this one is 6, I can find that one. 4 times 6 is 24. And divide by the 2. That tells us that had to be 12 amps. So that makes sense. It checks out. In an inverse relationship like that, it's a constant product. The last thing I want to go over is on the very last page of your packet. Problems 87 through 92. This is actually number 87 that I'm going to put up here right now. We have something like 8 ounces to 3 gallons. Now that is not a ratio, it is a rate because there's different units. Is equal to X ounces over 3 quarts. Well, looking at this, these are the same units, ounces to ounces. These are not the same units. I have to make them the same before I can cross multiply and divide. So 3 gallons times 4 is going to give us 12 quarts. So now I can cross multiply. 8 times 3 divided by 12 gives us, this is 2 ounces. I might have something, now this is not in the packet, but I might have something that's listed as 16 ounces per 5 square inches. And I want to know how many pounds that would be for 20 square feet. Well, obviously there's some issues here. What I'm going to do is this. I'm going to turn my 20 square feet into square inches. What's the conversion between square feet and square inches? 144. So times 144, that's 2,880 square inches. I'm going to find this up here in ounces first. Now I have the same unit there and there and the same unit there and there. So now I can cross multiply and divide. So 16 times 2880 divided by 5 gives us 9216 here. Well, that's in ounces. I want it in pounds. So to convert that back into pounds, I would divide by 60. 576 pounds. You guys should now be able to finish this packet. That's what I'd like you to do for tomorrow. Finish the packet. We'll have a little bit of time to go over some stuff tomorrow, but there also will be a quiz on problems that look suspiciously like problems in the packet. For those